María Camila es ingeniera y física de aquí de la Universidad de los Andes y muy comprometida también con la comunidad de Python. Por favor, démosle una bienvenida con un fuerte aplauso a María Camila Remolina.
Hola, mi charla va a ser en inglés, entonces cambiaré. Muchas gracias. So, today my talk is called Get Your Hyperparameters Right. So in machine learning, again, another machine learning talk, we have models, and sometimes they need hyperparameters, something external to it. So today we're going to learn how to select those, how to tune them to get our optimal result. So as Kuro said, my name is María Camila. I studied physics here with emphasis in astronomy. I did a lot of simulations, and parallel to it, I studied systems and computing engineering. I really like cryptography, but also software engineering and data science. So this merged into my two careers has led me to, well, where I am today, and I hope you like what I'm going to tell you. So to give you a bit of an outline, first we're going to learn what is this hyperparameter tuning, then how does SciPy help to solve this problem, like why am I here today in this conference. Then we'll see a practical example. So let's put this into a better context so we can understand it. And finally, just a take-home message, something for you to leave here with. So, well, the title is not appearing as I expected, but what is hyperparameter tuning? So the definition itself is choosing a set of optimal hyperparameters for a learning algorithm. So let's think of an analogy. I think of it like as a song. You have your machine learning model, and if you think of an equalizer, when you have a speaker and you want it to sound different, like this weighting of the frequencies that make your song sound better, that's what we want to get in the machine learning model. This perfect pitch, this good sound that is how, well, you want to predict or do something with your algorithm. When I say optimal, I mean that I want to minimize something. And something like a loss function, so maybe like minimize the error or maximize some expected result, something like that. So why does this word hyper comes into place? Like, what's the difference between a parameter and a hyperparameter? So in a model, a parameter is internal to it. It is necessary to determine the next result, to predict something, and it's often not set manually. The algorithm itself determines what it's going to be. However, a hyperparameter is something that cannot be deduced from data. When you have it, you need to set it externally in a manner. You can tune it, you can do it manually, you can do different ways, and it helps you estimate the parameters. It's like an extra tool that your model is going to need. So, and as an example, a parameter is something like a coefficient in a linear regression. Those A, B, or whatever, if you think about it in the simplest way. Instead, a hyperparameter, well, not in that same context, but in, for example, k nearest neighbors, that is also a simple model in machine learning, is that k, that external value that you need to, well, determine. So let's see that latest example to put this into place. Let's imagine we have some materials, some objects, and we can measure the pressure and the temperature. And we have a lot of experiments that we have done. So maybe we know that this one red that has these two values classified as a solid, but someone is a liquid and some other is a gas. So we think, okay, we already made a lot of experiments. Maybe we can do a machine learning model that if I get a new material, a new object, I can, well, say in which one of these categories is going to fall. So I'm going to do a nearest neighbors, k nearest neighbors algorithm. And the way it works, it's a linear classifier. So the way it works is going to try, wait, sorry. No, yes. So I thought I was missing a slide. It's going to get a new observation, and it's going to check the k nearest neighbors to it. So let's say k equals 1. So it says, okay, the closest thing to myself is this red point, so I may be a solid. And it's going to classify as that. But if I say, no, I don't want to see the first nearest neighbor, I want to see the 2 or the 3 or the 4. So if I choose 3, then as you see, I have 2 blues and 1 red. So now my material that before was classified as a solid, now is classified as a liquid. And if I choose an even larger k, it's going to go back to a red and become solid again in our classifier. So if you see, this K has a really important role in how the machine learning algorithm is going to predict results. So it's important to select it. So this leads us to the question, like, how do we determine this K? We have a lot of ways. There's a lot of different alternatives in the literature. First, we have it manually. Maybe we have a very good understanding of the problem. Maybe we know the scope, the context that we're talking about. So I can set it myself, and that's totally valid. There's another way that is a bit more extensive that is called the grid search. So I have something called a hyperparameter space. It sounds complicated, but it's just K is positive, right? You cannot have -1. So K goes from 0 to whatever you think is something reasonable. So that whole range is our parameter space, hyperparameter space, and we do an exhaustive search. We try each one of them and see how it does. Another one is the random search. We do the same thing, but instead of going through every single one of them, we select them randomly. So that has advantages or not. And finally, well, there are more, but the one that I want to focus about is the Bayesian optimization. So it's, you choose one, and that gives you a result. So now you choose another one, but you take into account the previous one that you chose to make a better estimation on that hyperparameter space. It's a lot about how we make decisions. If yesterday it rained, and the day before yesterday it rained, then today it might rain. There might be a slighter chance. I don't really know, but it's taking all of these previous experiences into account. So, well, I want to underline here this word optimization because, well, that's what we have SciPy for. So we have this, well, how does SciPy help? We have this huge ecosystem of optimization tools that we can use, well, to tune our algorithm. And the idea is very simple. Well, optimization, for everyone, you usually have this objective function, something that you want to minimize, maximize, or do something with that, and you will minimize it. In this case, we have, well, the objective functions takes into account the hyperparameters, the asset parameters, and then we put it in the model, we train it. Maybe I can point so that it's better. Yeah. So we train it, and then we make predictions. And we have this last function that we want to minimize. In our case, let's talk maybe the root mean square error, some sort of error. Whatever that's called an error, you want to put it to 0. So we just minimize this result. And that's it. It's as simple as that. So the idea is, you take a hyperparameter, an initial value. Usually, to all of these optimization tools, you put an initial value that is something you think might work, or you make some algorithm to choose it. You put it, you use your trained data, and you train your model. Then with another set of data called the validation set, you see how well it performed. And, well, in this case, the root mean square error. And, well, you go back again. This is the SciPy optimization tool. This is going to do, like, in a smart way to help you select and go through all the hyperparameter space instead of randomly or linearly, because sometimes in the grid search you may also miss some, well, the intersection between two values. Your better answer might be there. So this one does a better job. Well, that's it. However, sometimes, and for people who have done more complicated models, this training is very expensive. You cannot do it like 20,000 times. There are neural networks algorithm that takes days of running. So you have to choose the smartest way possible and go through your space and call this function the least amount of times. So in our model, we have something like this before. So as I want to reduce this number of calls, we're going to do something a little bit different. This is going a step further. With everything that I told you about SciPy so far, you're good. Like, that's already a very good approach to what has been done previously. But now, as this is very expensive, we're going to treat it as a black box. Something like, you put an input to it, you get a result, but you don't know how it behaves. But we're going to use Bayesian probability, so we're going to make an assumption that this function, this black box that you have, might have been sampled from a Gaussian process, and that it maintains its distribution with every new observation. It sounds a lot like probability and statistics. I just wanted you to get the general idea. But what it does is what I told you before. It takes into account all the previous evaluations, and and it takes a smarter new value. So now, instead of this cycle that was going to be the SciPy best decision, we're going to create something called a surrogate. So we want a function it's similar to a machine learning model, and that in a very quick way can tell you, oh, maybe the result is going to be something around it. And based on that result and the history that you have another function that's called the selection function that will choose your next hyperparameter. So this is a bit of an alternative of the SciPy optimization cycle, but it's a very good one, and one that I think is the best one for models that take a lot of time and are very expensive to compute. Well, just to be more technical, the surrogate is the probability representation of that objective function, and the selection function is the criteria by which you choose the next set for the next loop. But well, this is a very deep topic. We can talk about it later. There are different, within each one of these, there are different types, like the TPE, or for the selection function, something called expected improvement. That's going a bit deeper, but that's the whole general idea. And well, there are a lot of libraries, like in Python, you don't have to start from the bottom. A lot of people have done a lot of work with this. So there's Spermit, MOE, and well, a lot of different libraries that help you go this step more from the SciPy optimization. So let's put this into practice. It was a lot of theory, a lot of statistics. Let's think about a practical example. So I'm going to show you this project that I did in the past. So the idea is we're going to take a corpus, a data set that is full of words. We take them from books, from Wikipedia, from newspapers, and we have them classified. So for each word, we know it's part of speech. This sounds complicated, but it's just, oh, this word is a noun, is a verb, is an adjective, is these names that we put, these categories that we put words in linguistics, and we have them tagged. So the idea is that whenever you get a new word, you want to determine if it's an adjective, a verb, an article, or something like that. However, we're going to shift it a little bit. The objective that we train it with all of this data set of books and very well-written things. Now we're going to change to tweets, to forums, to chat messages, to something that it's not going to strictly follow the rules of how we write, well, how we should write according to linguistics, but we move to like a more practical, natural way of speaking. Well, that's the objective. Our machine learning model is going to classify these new words. So in this case, well, this moved a lot from what I had it, but I think you can still see it. The algorithm will be a multi-class averaged perceptron. This is just the name. It's like KNN. And it is a linear classifier. So it tries to take all of the words. Imagine these dots are the words. Each one of the colors is what it is classified in, and it's going to try to divide them into areas, into different zones, into space, according to different features that we define. So, for example, if it's a noun, I think a good feature for that word would be maybe it started with a capital letter. I don't know, that could give me information. Or the length of the word, of the prefix. If it's a verb, you can get the same prefix, but a lot of different conjugations. So that could also be one key feature. Or there are words that are around it, the context itself. So we take this feature vector, but think about it just like a collection of things that determine the characteristics of the word. And as you think that for each class, these features, someone imports more than other, it has more importance, then, well, each class will have a different weight. The idea of the perceptron of this algorithm is that it's going to give those weights. Each iteration is going to improve them and to get better. So let's see it visually. So we have all the words, and at the first iteration, it does the first epoch, it says, okay, I'm going to divide them like this. But well, that doesn't seem right. Like there's a lot of 3 different categories here, only 1 here, and 2 here. So we can see it visually that it should not be there. So it continues, and it improves because it takes into account the previous one, right? It improves, it keeps going until you have an epoch, you reach a maximum epoch end. But as you see, depending on the epoch, it changed a lot, the division of the space. So this is, in fact, well, a hyperparameter that we want to tune, that we want to determine what it is. So in the end, what the average perceptron does is that it's going to average all of those different divisions that we made. and determine, well, this is going to be, whatever word that falls here is going to be a noun. I forgot the categories. So yeah, that's it. And how would this be solved with the technique that I told you before? It's super simple. So the objective function is the same, just now our machine learning model is going to be, well, the average perceptron. We're going to, well, train the data set, make a prediction, and just calculate the error and minimize that. So it's literally as simple as just importing from SciPy, optimize, and minimize that objective function. This minimize has a lot of different parameters that you can put in, like a specific method. Maybe you want to use, well, in your context or in your algorithm, there are different alternatives for finding this minimum. Like in, well, optimization is a huge area of research, so there are a lot of these. You have the initial epoch, and you have a lot more values that you can tune. So this is also, in some sort of way, some hyperparameter tuning. But it's something that you can put more logic into it. And there are a lot of different heuristics that can help you take this decision. But it's as simple as that. Just you run it, and then it will finish the optimization after it explored the space. And it will say, okay, I think your best number of epochs should be 15. That should minimize your error next to the validation set. And then when you measure the quality of your algorithm, you think yet another set. And see how it performs there. But that's it. So I want you to take home the message that you don't have to put them manually. Sometimes especially I think when we're starting in machine learning, this is so many choices that you get, like this hyperparameter or even the algorithm itself. It supervises and supervises what should I do. So this is like a tool so that you don't worry that much about that. And when you get a better understanding of your problem or your model of everything, well, you can put a little bit more tuning into this. You can also set your objective function to limit the space if you think that there are some specific regions that it should go to, or put a probability function there. You can put it more complicated, but if you're just starting, and if you want to use, for example, k-nearest neighbors, this is it. And if your model doesn't take that much time to run. So today I learned, in case that SciPy has a lot of tools that will help you tune your models, your machine learning models, and find this balance between exploration and exploitation. Because you still need to explore the space. You cannot just magically appear the value. You need to run your model, you need to train it. But there are smart ways for choosing them and for exploring that huge space that will optimize your time, your machine learning model, and, well, in the end, the result that you want to get. So that was it. Thank you. So if you have any questions, I'm here. Everyone wants to eat, right?
You mentioned at some point that you were using SciPy optimize and another method, but in your result you only show SciPy optimize. So could you talk a little bit about the other method? Sure.
In this case, well, the k-nearest neighbor is really fast, so you can do and I wanted to show a simpler approach for this. So yeah, you can do it because it was, I don't know, it took like an hour. No, I think less actually. I just forgot, but it's something that you can get straightforward, so you don't need to put this very complicated method. However, the libraries are also very simple. These ones that I put there work very similar. Like, you just put the model and it takes care of all of this surrogate function and the selection function. Something to clarify in the last part that you made me realize I forgot to say. In this case, in the perceptron, in the perceptron, the number of epochs is an integer, so that moves you a bit to the domain of integer programming and integer optimization. So you have to be a bit careful when you have integer parameters that you want to optimize with this method, but you can tweak it like I did. You can have something that casted or that modifies a bit the probability that you're going to get, the value that you're going to get. But yeah, I just wanted to show the simpler approach. But the other one is also straightforward. It's not that complicated.
Thank you.
essentially, in your experience, do you have any practices? Maybe this is an optimization question, but essentially to prevent being in a local minimum. I mean, get trapped in a local minimum.
Usually, is that method you saw here, that desired method? Well, you can also. I'm not an expert in optimization either, but you can estimate what your probability function looks like, how it should be, and these methods try to avoid finding local minimums or try to avoid hitting extreme points where you just go out of range. So it depends. It goes a bit. It takes you a bit of time to read not a bit of time, like short time to read the description of, or maybe what is the best method for what you want to do. But it depends on the case. Yeah, so I don't really know. I think just going through the main ones or maybe trying different ones and see how it changes. But yeah, maybe Carlos knows more about that.
Thank you.
When you try the other way to get the K you were talking about, you said you have a function that has probability or something like that. How do you, like, with the results you get before, how do you, like, rebuild that probability function, or you don't take it into account?
Well, with the libraries themselves, they take care of it, so you don't really define the function. You just put your model and it starts to estimate it. So it's more like I don't want to say black box because you can go into it, but you don't really get like a formula in the end for that. So it doesn't really compare that much to a model, but you do get a similar, I got the same hyperparameter.
And for example, when the library itself, like, take into account the results that you want to estimate?
Yes.
The results become parameters too?
Yes, exactly. You have something called like a history. So whenever you run it, you get like a score and hyperparameter tuple. And it just starts recording, and based on all of that records that you get, you will get a final iteration and take a better decision each time.
Anyone else?
Thank you. Well, thank you, everyone.